depreciation. And in fact, depreciation works very, very similarly to appreciation, which happens in compound interest, which is what we just looked at, except now the value of whatever you have is depreciating. It's going down, okay? And you don't want this to happen with an investment. Sometimes it does. You don't want it over the long term to happen with an investment. But if you buy, usually it's like some sort of electronic. As soon as you buy it and open it and start to use it, it is depreciated in value, right? So if you've ever tried to sell an old phone or camera, or cameras have been a little bit obsolete now, or even a used car, that's where you might see a depreciation situation, okay? So here we go. Gina bought a camera for her studio 2 years ago. Her accountant told her that she can claim a depreciation rate of 20% for the camera as a business expense. We'll talk about that in a second. At new, Gina's camera is worth $2,500. The function V equals 2,500 times 0.8 to the x, where V is the value of the camera after 8x years, can be used to model this situation. For how long to the nearest tenth of a year will it take the camera to be worth only $200? Okay, so let's just talk about a little things that are going on here. So firstly, she bought a camera 2 years ago. She bought it new for $2,500. Her accountant tells her that she can claim a 20% depreciation rate for the camera as a business expense. Okay, so let's pick that apart firstly. So 20% depreciation per year, what does that mean about the value of the camera? Yeah, it's going down. The value goes down every year by 20% of what it's worth that year. Yeah, okay? So let's just make this simple. If it's worth $100 new, the next year it's going to be worth $80. The year after that, it's going to be worth 80% of 80, right? If it's losing 20% of its value, it's retaining 80% of its value, okay? What is this business about a business expense? Do you guys know what that's all about? When you're doing taxes? Probably not yet, but maybe you've heard your parents talk about it. Yeah? Yeah, so it has to do with income tax, right? It's when, so you pay income tax on not all of your income, but something called taxable income, right? So if I earn, let's say, $50,000 a year, okay? But I have to spend $10,000 to make that money on business expenses. Like, for example, maybe I have to drive around a lot and I have to pay for my car. Or maybe I have to buy supplies. Or maybe I have to whatever. I have to spend money in order to make that income. Then that's actually not taxable in my income tax. So if your income tax is, I don't know, 40%, you're going to pay 40% of $40,000 instead of 40% of $50,000. Okay, and you can hear it be claimed as tax deductible. You may have heard that phrase before. And that basically just means that you take your income, you deduct these expenses, and now you don't pay tax on that. A couple of other things that are tax deductible, these wouldn't be business expenses, by the way, but I think they're interesting, is when you pay for schooling, post-secondary education costs, you don't pay tax on that. You don't pay tax on childcare. You don't pay tax on charitable donations, okay? And the reason really is that the government wants to encourage people to go to school, because typically when people go to school, they make more money. And if they make more money, it means that in the long term, the economy is going to be much stronger, right? If they make childcare tax deductible, then people will, instead of staying home with their children, will put them in daycare or get a nanny or something, then they're going to go out and work and make money. And the country is stronger when more people in the economy are earning more money, right? The charitable donations are tax deductible because they want to encourage people to donate to charity, and then that might be something that the government doesn't have to supplement anymore if there are members of the community donating instead, right? So it's very political in terms of what's tax deductible and what's not. Anyway, I went on a little bit of a tangent. Let's go back to this question. But I do think that it's worth having these discussions around particularly finances, because I think it is a neglected area in the high school curriculum. Okay? All right, so camera's losing 20% of its value from the year before. If it's losing 20% of its value, how much of its value does it retain? 80%. Okay? So this is where this equation comes from. V equals, I want to go back to black, 2,500 times 0.8 to the x. This is your principal amount. How much did you put in initially for this camera? You can think of this almost as the initial investment. Okay? This guy, 0.8, comes from 1 minus 0.2, right? The 1 represents 100% of its value, but then you take away 20% because it's depreciating. So in the previous example, we had to add an interest rate because it was appreciating, it was getting bigger. If it's depreciating, we have to take that away, right? And then to the x means, okay, well, every time a year passes, we have to multiply by 0.8 over and over and over and over again, okay? So here, the question is, how long to the nearest tenth of a year will it take for the camera to be worth only $200, okay? Well, which of the two unknowns? You've got two unknowns, value and x's time. Do we know in this case? What's that?
Yeah, we have the value.
Yeah, we have the value, right? That's $200. So we're going to plug that in for V. And now we can solve for x. Okay? Now you can solve this graphically. So if I pull out my graphing calculator, then I'm going to enter essentially y1 equals 200, and y2 equals 2,500 times 0.8 to the x. I'm going to try and find an intersection point. Where did that calculator go? Oh, there it is. Okay. All right, so here we go. $200. And then this one was 2,500 times 0.8 to the power x. Okay. Now, the challenge when solving graphically, again, is the window settings. So you got to be clear about what these two things mean. Y represents the value of the camera. So firstly, is the value going up or down? Down. And what's its highest value? 2,500. So if we're thinking about our window settings, right, then the minimum value of the camera is 0. The maximum in this case is 2,500. So maybe I'll make this actually 3,000 just to overshoot a little bit. Okay? Our x values are time in years. So think, what's the minimum time that she can own the camera for? 0. What about maximum time? How long do you think someone might own a camera for? How long do we want to track this for? 25 years? Sure. And then we're going to go graph. And there we go. That's actually a really good window setting. Okay, so we can see here's the camera's value. It's depreciating. And then here's the time where it's worth $200. Okay, so I'm going to graph that. Draw a sketch. And it looks kind of like this. Okay, and my window settings were 0, 25, 1, and 0, 3,000, 1,000, I think, was the scale. And then I can go and find that point. All right, so back to the calculator. Second trace 5. That's pretty close. And here we go. What did it say to round to? It's 11.32 to the nearest year. Okay, so this is 11.3. $200. So I would say takes about 11 years to be worth $200. Okay, now this one is actually a fairly straightforward one to solve with logarithms. You can solve it algebraically as well. So I want to review that once, but I also want you guys to know that for these problems, you can always solve these application problems graphically for logs and exponents. Okay, so to solve it algebraically, maybe I'll do this in a different color. It's a good review of using logs to solve exponential equations. Okay, so when we use logs, we typically take logs of both sides. But before you do that, you want to make sure that the power has been isolated. So what I'm going to do is I'm going to divide both sides by 2,500. And 2,500, I'm just doing this on a calculator, or 200 rather, divided by 2,500 is 0.08. Equals 0.8 to the x. Okay? If I take logs of both sides now, let me give myself a little bit more room. I can bring this guy out front. So I'm going to get the log of 0.08 equals x times the log of 0.8. Okay, and then to solve for x, I just divide both sides by 0.8. Or not 0.8, but the log of 0.8. Okay, so we should get the same answer, hopefully. Otherwise, there's a mistake in there. Okay, log of 0.08 divided by the log of 0.8 equals, yep, there we go, 11.3. Okay, but again, not expected to solve algebraically. What I would actually say is even more important is that you can kind of explain all of the different parts of the equation. What does the $2,500 represent? What does the 0.8 represent? Okay. That's an important concept. Okay. Let's talk about pH. How many people have seen pH before? pH scale. Okay. So what can you tell me about it? What is pH? What does it measure? Yep.
How acidic something is?
Yes, how acidic a solution is. And the atom that makes, or the molecule, the ion actually I should say, because it's missing, what is it missing? It's missing an electron, I think. Guys, it's been a really long time since I did chemistry. But the ion that makes something acidic is hydronium. It's H+. Okay? So really, when we're trying to measure how acidic something is, we want to know what is that hydronium ion concentration. The more hydronium there is in a solution, the more acidic it will be. And the less, do you guys know what something's called when it's not acidic? Basic, right. Okay. And what does the scale, what are the numbers on the scale? 1 to 14, yeah. Or is it even 0 to 14? I don't know. Can't remember. Maybe 0 to 14? 0 to 14, okay. Yeah, so and if you're more acidic, where are you going to be on that scale? Lower, yes. The lower you are on the scale, the more acidic you are. The higher you are, the more basic you are. Okay? So pH is not the concentration of hydronium in the solution. And the reason why it's not that is that the concentration of hydronium is very, very, very small usually because it's a percentage of the total solution. So let's say you take lemon juice and you pour it into water. It's not going to be 100% hydronium, right? It's not going to be 100% acid. It's going to be diluted. And there is a massive range of values that you can get for that concentration. It could be a teeny, teeny, tiny amount, or it can be quite a high amount of acid in that solution. And so it's inconvenient to keep track of the concentration of the solution. And even if we did, we'd have decimal values that are like 0.000, lots of zeros and then a number. And that's not very convenient because it's hard to remember, and we often make mistakes writing those things down, and so on and so forth. So what I guess chemists decide to do is, they said, you know what, we're going to measure this on a logarithmic scale instead. And we're going to say that pH is going to be the negative exponent value on that concentration. So you can see here, pH equals negative log x, where x is the concentration of hydronium ions, okay? And that's the relationship between pH and concentration. The pH is actually the negative exponent on that concentration, okay? So for example, the hydrogen ion concentration X of a solution is 0.0001 moles per liter. That's right. I forgot. It's not given in terms of percentages. Oh, it's been so long. It's been given in terms of how many moles per liter. Do you guys know what a mole is? Yes? It's 10 times, no, it's like there's a day in October. Isn't it 2 point something times 10 to the negative? Oh man, this is embarrassing, and I'm recording. I can't remember. But it's a really large number of atoms, basically, is a mole. It's a number of atoms. Okay? There we go. Let's leave it at that. And it's a large number of atoms. 10 to the 26. 23. Yeah. 23? Are you looking it up? What is it? It's October 23rd. Yes. 10 to the 23, is that it? Okay. All right, cool. There we go. I knew it was October. There's a day in October. I knew there was a 10 in there somewhere. Okay. So let's say we have a concentration of a solution. The concentration is 0.0001 moles per liter. We want to know the pH of the solution. So we have this equation, pH, or P of x, equals negative log x. And this is the concentration of hydronium ions. Have you guys seen this notation before? This I remember. Yes? So in chemistry, when you have those square brackets, you're referring to the concentration of something. And H plus is the symbol we use for hydronium ions. Okay? It's just it's positive because it's missing an electron. Okay, so we know here what that concentration is. So if we want to know the pH, it's going to be negative log of 0.0001. And I believe that's 4. Is that 4? This calculator's not working. What is it, guys? It's 4? Okay. Okay. So why is it 4? How did I know that? I knew it because this over here is 1/10,000th. And 1/10,000th is 10 to the negative 4. So log of 1/10,000th is -4. If you stick a negative sign in front of it, -4 is +4. And that's essentially why we have a negative sign in front of the logarithm. Because chemists decided, you know what? We don't want to use a negative scale. We don't want the values to go from -14 to 0. We want them to go from 0 to 14. And so that's why that negative sign is there in front of it. Okay? All right, so if you know the concentration, it's as simple as that. Okay? Now, the important thing to think about, though, is that 4 is not the concentration. It's the exponent, the negative exponent, actually, on the concentration. Okay? All right, let's look at this guy. Calculate the hydrogen ion concentration of lemon juice, which has a pH of 2. I knew lemon juice was pretty acidic. Okay, so here, we have this relationship. And this time we know the pH. We don't know the concentration. So we're going to put a 2 in here. Need to solve for x here. What do you think a strategy would be? Working with logarithms. What do you think we could do? What's that? Well, we can't exactly just take the log of this without changing that. We could go log 2 equals log of logative negative x, but that doesn't help us to isolate the x. So the problem with dividing by negative log, I love that you're coming up with ideas. That's awesome. I wish more people would do that. The problem with dividing by log, dividing by log, is that log is not a variable. It's like attached to a number, a numerical value, right? So think about how would you even put this in your calculator, 2 divided by negative log. As soon as you put a log in your calculator, it opens up a bracket for you to put a number in there. Yep. Okay, yes, so you could graph it, absolutely. You can absolutely graph this, y1 equals 2, y2 equals negative log x. That's no problem. But I want to think about another thing. What do we connect logarithms to? What did we study right before logarithms? Exponents. Every logarithm can be written in exponential form, right? Now, problem is you do not want to switch forms until your log is isolated. And right now, this is negative log. So I'm going to multiply both sides by -1. If this is negative, this is positive. If this is negative, this side's positive. Make sense so far? What is the base of this logarithm? 10. Okay, so if we now switch to exponential form, what would the base of our exponent be? 10. What is the exponent? -2 equals x. And 10 to the -2 is 1 over 10 squared, or you could put that in your calculator, 0.01 moles per liter. 10 to the -2 is 0.01. Okay? The mistake that I get people making sometimes when they try these questions, because this comes up all the time. I've seen it on lots of diploma exams, lots of unit tests, stuff like that. Because it's a really common application. It's one of the most well-known applications of logarithms that people know about. The biggest mistake is that people try to switch forms without making the logarithm positive first. Okay? And that's super important. You got to make sure that that's positive. When in doubt, though, solve graphically, right? So you could, for sure, just write y1 equals 2, y2 equals negative log x, find the intersection point. Okay? All right. Part C, in terms of hydrogen ion concentration, how much more acidic is solution A with a pH of 1.6 than solution B with a pH of 2.5? Round to the nearest tenth. Okay. So how much more acidic is solution A than B? So here's what a lot of people do. They go 2.5 divided by 1.6. Okay? And it's a common mistake because we're kind of used to doing that. If I said one person can run 5 kilometers an hour and another person can run 15 kilometers an hour, how much faster does the faster person run than the slower person? You go 15 divided by 5. So if you want to know how much more acidic, makes sense, oh, I just go 2.5 divided by 1.6. But that is incorrect because pH, remember, is not the actual concentration. Okay? The pH is the negative log of the concentration. So you cannot compare how much more acidic one thing is than another unless you know the specific concentrations. So what we need to do is we need the concentration of hydronium ions in each solution. Okay, so for A, we know that the pH is 1.6. So we're going to get 1.6 equals negative log X. Okay. Now, once you do these problems repetitively, you're going to start to see that there are patterns that make it go a lot faster. Because when we solved this previous problem, the actual X value was 10 to the negative pH, right? So if you do it a little bit, you can take some shortcuts. Okay, but if we rearrange, we're going to get negative 1.6 equals log X. And then to solve for X, we can switch forms. So X, again, is the base is 10. The exponent is negative 1.6, and that's equal to X. Okay, so that's the concentration of solution A. For solution B, that has a pH of 2.5. Okay. Well, once you've kind of done this first one, you can see where the X comes from. It's 10 to the negative pH. Okay, so here, X is going to be 10 to the negative 2.5. That's the concentration. Okay. Now the question is, how much more acidic is A than B? We have to take concentration of A divided by concentration of B. Okay? So to compare, you want to go concentration of A over concentration of B. And that is 10 to the negative 1.6 over 10 to the negative 2.5. And I don't know what that is. It's 7.94, round to the nearest. .4 times more acidic. That's a big difference. For less than 1 value change in pH, it's 7.9 times more acidic. There's 7.9 times more hydronium ions, right? And in fact, because remember, the pH is the exponent on base 10, every time the pH goes down by 1, because lower is more acidic, the acidity increases tenfold. If it goes down by 2, it increases 100-fold. If it goes down by 3, it increases 1,000-fold. And the Richter scale, by the way, works the same way. Okay? All right. I think we have 2 more. We may be able to squeeze them in. Application 5, decibel scale. So loudness is measured in decibels. The formula for the loudness of a sound is given by the formula dB equals 10 log I over I naught, where I over I naught is the intensity ratio of the sound. If a cat's purr is about 316 times as intense as the threshold sound, what is the decibel rating to the nearest decibel of the cat's purr? Okay, so this question, this type of application I've seen people get tripped up with this because if you look at the equation, it kind of looks like there is 1, 2, 3 variables. Can you guys see that? Yes? Yeah. Yeah, so that's the thing, right? I over I naught is a ratio. Okay, so you may not actually need to know the actual values to know the ratio. If you see the words something times as intense, that is a ratio, right? If I said 2 times as much, we don't actually need to know what the much is. We just know that one is 2 times greater than the other. That's a ratio. So although it looks like there's 2 variables, and sometimes there might be, right, if I don't actually have the ratio, but I just have 2 different decibel ratings. But if you see this language, this word also indicates a ratio. And so we can replace that entire I over I naught with 316. Okay, so that's kind of the tricky part to this one. So here we're going to get dB equals 10 log 360. That's it. That's all there is to that one. So I don't know. It's going to be 2 point something, or 20 point. 20 point something, I think. 20 something. 10 times the log 316. 24.996 whatever. So this I would say is 25 decibels. All right. Last question. Richter scale, the Richter scale. Okay, so I've mentioned this before. A Richter scale reading is not the intensity of the earthquake, but the exponent on base 10 of that intensity. So if you have a Richter scale of 2, the intensity of the earthquake is 10 squared, or 100. If you have a Richter scale reading of 5, the intensity of the earthquake is 10 to the 5, or 100,000, I think. Is that 100,000? I think it's 100,000. Okay? But the difference in those intensities is 10 cubed. It's 1,000 times more intense, even though you only go up by 3 points. Okay, so in 2010, the 2010 earthquake in Haiti measured 7.0 on the Richter scale. In 2004, an earthquake off Indonesia measured 9.1 on the same scale, and caused a tsunami. In order to compare the relative intensities I of these 2 earthquakes, the following formula may be used. I, which is the comparison of the intensities, equals 10 to the m over 10 to the n, where m and n are Richter scale values for each earthquake. Compare the 2 earthquakes to the earthquake in Haiti. The earthquake off Indonesia to the nearest whole number is how many times stronger? Okay, so remember the Richter scale reading is 9.1, but the intensity is 10 to the 9.1. And in Haiti, the Richter scale reading is 7, but the intensity is 10 to the 7. So if we want to compare their intensities, and this is the intensity comparison. It's going to be the intensity of the bigger one divided by the intensity of the smaller one, which is 10 to the 9.1 over 10 to the 7. Okay, now you could plug that into your calculator, but let's just review exponent laws here. We have 2 powers with the same base. What do we do to their exponents? Subtract. So that's 10 to the 2.1. Okay, now think. That's between 10 squared and 10 cubed. So what's 10 squared? 100. 10 cubed? 1,000. So it's going to be like, I don't know, somewhere between 100 and 1,000 times more intense. Probably closer to 100. Okay, so I'm just kind of verbalizing estimation strategies there, but you could certainly just enter that into your calculator. There you go. It's about, to the nearest whole number, I think it asks, 126 times more intense. Yeah. Okay. I actually remember that in 2004 when that earthquake happened. And I remember it, like, I kind of think about this because back then, like, the internet was very, very small. People did not get news on the internet. And this happened in December around Christmas time. And I was on vacation. And we didn't have access to internet. We didn't really watch news while we were there. And so this thing happened. Thousands and thousands of people died, mainly because of the tsunami, actually. And we didn't find out about it for like 10 days because we just didn't pay attention to the news, which is kind of nice. I wish we could go back to that. But it was a devastating, devastating event. And it wiped out all of the coastal cities, just got destroyed. All right, let's end on that note.